All right, so here we go. Now we're going to talk about something a little bit different. Now we're going to talk about how we actually measure heat change in the lab and where this comes from and how we do examples of it. Okay, and so this is called calorimetry. So calor is a Greek unit for heat, and itry is the science of, or the heat of. And so this is measuring heat flow from reactions. And so we use a device called a calorimeter to do so. In our class, we're going to use essentially styrofoam cups that are nested. There are commercial versions available, but I don't have them, and they're really expensive, so we don't use them. Okay? And so we're going to perform these calculations under constant pressure. Whoop. Okay. Where'd you go? Under constant pressure conditions, and because that'll make the math easier for us. And so constant pressure conditions, as it simplifies the math considerably. So before we can do calorimetry, though, we need to understand some other terms and the calculations that are involved. Okay? And so heat capacity is the first thing that we need to talk about. And so heat capacity is the temperature change that an object has when it absorbs energy, or it is better defined as the amount of heat needed to raise the temperature of the object by 1 degree Kelvin or 1 degree Celsius. Okay, I know that this might be confusing. I'm going to explain that in just a little bit, so hang on with that. But heat capacity is how much energy it takes to change something's temperature. We've all had examples where we've seen objects that contain change temperature take a long time. You know, a pot of water boiling on the stove takes forever to get to a boil. We all know that. Whereas, you know, an empty aluminum can sitting on your stove would reach that same temperature much faster. And so, well, that's got to do with its heat capacity. How much energy does it take to change the temperature of that? All right. So in a pure substance, we use a version of this number that specifies an amount. This is the molar heat capacity. And so the molar heat capacity has the Cm here, C sub m. And it's the amount of heat required to change the temperature of 1 mole of that substance by 1 degree. Excuse me. The specific heat capacity, it's funny that I left the S there, or CS, is the amount of energy required to change the temperature of 1 gram of that substance by 1 degree. We're going to use both of these numbers, okay? So specific heat equals the quantity of heat transferred divided by the grams of the substance times the temperature change. And so we could write that as CS is going to equal Q divided by M divided by T. Okay, so grams of substance, that's mass, right here. So I didn't really define these anywhere but right here, but they are there, okay? And so this is delta T, change in temperature. For regular water, it takes 209 joules of energy to increase the temperature of 50 grams of water by 1 degree K. So, okay, CS is equal to Q, the amount of energy, 209, divided by its mass, 50 grams, times 1. So 209 divided by 50 times 1 is equal to 4.18 joules per gram degree Kelvin. This is the specific heat capacity of water. Now, this is a big number, actually. As far as specific heat capacities go, this is a pretty big number. Okay? And so that means that it takes a lot of energy to change the temperature of water. Because the value of this number is as big as it is, it takes lots of energy to change the temp of water. And that's a big deal, okay? We know that that's a big deal because water is what modulates our temperatures and on our planet, and it has a lot to do with our weather, and so that's a really nice, useful thing for us, okay? So, here we go. So let's talk about a little bit more as we move forward here. So I gotta erase this and get you guys a clean slate to continue. So here we go. Okay, so let's scroll this up, and there we go. So this is the specific heat capacity of water. And like I said, that's a number that we're going to use a ton. So the change in degrees Celsius equals the change in degrees K. So I said I was going to explain that, and here I am. As they are they're the same size unit. Okay, so a temperature Kelvin and a temperature in degrees Celsius is the same magnitude of unit. Okay, the only difference between them is the location of their zero, and so location of zero. Okay, and so I'm going to do my best at drawing a really yucky diagram because that's what I'm good at. But let's say this is degrees Celsius, this is degrees Kelvin, okay? I'm going to say this is 100 degrees Celsius. On Kelvin, it's going to be 273. I don't think you can read that, so I'll write it right here. That's 273. So if I do a straight line down, all right, so this is boiling point of water. Okay, 100 degrees, water boils at 273 K. Freezes at 0 degrees Celsius, so this is the freezing point of water, so freezing point. And there, well, here we're 100 degrees lower, this is 173 K. Okay, now if we broke those up into 100 even units, they would be the same size unit because this is 100 to 0, this is 273 to 173. 0 on our boiling scale, on our Celsius scale, is where water freezes. Now, if we go all the way down here, though, to 0 on our Kelvin scale, we are at negative 273 Celsius, and this is absolute 0. Okay, and so that's the difference here. That is the difference between Celsius and K. They're the same size unit. Each unit is the same piece of temperature change, but the only real difference is that 0 on Celsius is where water freezes, and 0 on Kelvin is where absolute 0 is, and all molecular motion stops. Okay, so that's what this is, and just to help you guys with that a little bit. Okay, and so the temperature must be very clearly specified when we use this equation. We got to make sure that we're in one of those units and we're working through it to do what we need to do. Okay. Now we can rearrange the above form to this. Q is equal to CS times M times delta T. That is an excellent equation. We're going to use the crap out of it. So if a sample increases in temperature, well, that means that we have a positive Q value. Okay, if T decreases, that means that Q is going to be negative. And it doesn't matter what direction the heat change is, we can still use this equation. We just got to be cautious about our zeros and using negative signs. So I would say that we have to be careful of our negative signs, because otherwise we might get ourselves in trouble. Other than that, it works pretty good either way. Okay. Now we're going to set up a sample problem here. And here we go. So how much energy is released when a sample of 47 grams of nitrogen gas is cooled from a temperature of 200 Kelvin to 125 degrees K? And so the equations that we need, we're going to need Q equals CS times M times change in T. And we need to know that delta T is equal to T final minus T initial. And our CS, I have to give you this value because you don't know where it's coming from, is 1.04 joules per gram K. Okay, so this is going to either be given specifically in the problem, or you will have a table to find that information. Okay, unless I'm asking for you to solve for this, and I'll have to give you the other variables or ways to find those other variables. Okay, and I'm going to do that to you. I'm going to challenge you, and I'm going to make you reach a little bit and try and figure out how it's going. So just so you know, that's going to happen. So all right, let's get all this mess out of the way. Let's do a sample problem and get you guys on your way with this one too. So here we go. I left a blue streak right there. All right, next page. Here we go. Okay, so here's our sample. Let's go. So we needed the equation Q equals CSM delta T. We need our delta T. So let's find what delta T is first. All right. So Q is equal to CSM m delta T. And we need to know that delta T is going to be T final minus T initial. Initial, IN, yeah, whatever. Spelling, it's not just for breakfast anymore. Let's get to this and do it. All right, so our temperature or our sample here, we started, our gases cooled from 200K to 125K. So delta T is T final minus T initial. So T final is 125K minus 200K. And so that's a negative 75K. Okay. Kept my negative there. I need that there, and I need to keep it together so I don't screw it up down the road. So that's what I'm talking about with being cautious about my units, okay? So Q is CS times M times delta T. Okay? My CS, my specific heat capacity for nitrogen gas, is going to be 1.04. So 1.04 joules per gram times degree K, or Kelvin. Okay, and with Kelvin we don't actually use the degree sign, so that's why I erased it. Okay, so be cautious about that. So 1.04 times that. Now we need our mass. There were 47 grams of nitrogen gas, 47.0 grams, and okay. And the last thing we needed was our delta T, which is negative 75K. Okay, now let's do some dimensional analysis thinking to find out what unit we're going to get. Okay, so this is a Q. So we gosh darn better get a unit of joules when we're done with this, or some unit of energy. So joules or kilojoules is what we need to get out of this when we're all said and done. Otherwise, we will have all kinds of problems, and it's just not going to be happy. Okay, so let's cross units off. So I have grams here. This is in the numerator. I can put this over 1 to show you that. Okay, so grams is in the numerator. Here I have grams in the denominator, so the units of grams drop out. Same thing with Kelvin, numerator, denominator, so that is gone. So this is going to leave behind me just a unit of joules. Excellent. That means that we set it up right. We multiplied the pieces right, because all we have to do is multiply that times that times that, and it's going to leave behind a unit of joules. Okay? Engage your cognitive dimensional analysis brain to make sure that you can do this, to make sure that you're treating the numbers correctly. Okay? Because then I can't mess you up on other stuff. Because if you can set the units correctly, you know what you're going to get. So do that, okay? All right, 104 times 47 times negative 75. We should get negative 3666 joules of energy being released. Okay, so this is a negative sign. Okay, released. There's two ways to say there and there that this is exothermic. Okay, so that is an exothermic reaction. We're taking heat out of that hot gas, we're cooling it down, and so the energy is being released out. So that's it. That's the basics of working with calorimetry. We're going to spend lots of time working through this in class. I think we've got a lab or two, a couple of activities that we're going to work through. So if it doesn't make sense just yet, it will in class. So talk to you soon. Bye.